Cool. So tonight we're moving beyond single phase, and we're going to start looking at polyphase, or more commonly three-phase power. So it's the system used across New Zealand for generation and transmission, as some of you guys surely know. And before we dive in, so let's do a little bit of a recap. So what are the limitations of single-phase supply? What do you guys think the limitations of our single-phase supply would be? Yeah, we can only run a single phase load. Can't share current loads, yep. Only up to 230 volts, yeah. Well, yeah, we can't use three-phase motors on single phase. Yeah, figured that's what you mean, Andy. Okay, so basically, it's less efficient over distance. So we have less pressure at the 230 volts, and it's less efficient over shorter distances because we can't really crank it up beyond to that so many thousand volts that we need to. We get more volt drop if we only use single phase. It has a limited power capacity, so we don't have the capacity to use as much actual real power. And we need more equipment for rotating machines. So if any of you guys have worked with motors, you'll know that a lot of single-phase motors require extra equipment, whether that be capacitors or other special forms of making them operate at single phase, or we have to use a specialty variable speed drive or drive that takes our 230, converts it into DC, converts that DC into three-phase, and then we can run our motor, which obviously is not very efficient. Cool. So when we talk about polyphase, it's two or more phases. So anything, it's either single or polyphase, because you can have two-phase machines. And obviously in New Zealand, we use three-phase for the grid. Cool. So three-phase generation is more efficient over distance. It reduces volt drop. So we don't have as much volt drop over such long distances. We have increased power capacity and more simple construction for our rotating machines. Cool. So single phase generation. It is out there. So this is an example of what you would find inside of a single phase two-winding generator. So as you can see, it's a loop of wire with two coils connected to a, well, it's positive and negative on this side, but really it would be phase and neutral. So obviously we have to spin that motor 180 degrees before we get another change in the sine wave. So we're only seeing a rise, one complete sine wave every 360 degrees. So this is what our waveform looks like. So single sine wave, which we've talked about before, going up to peak voltage at 90, zero at 180, peak inverse voltage at 270, and then back to zero at 360. This is stuff we've all gone over in year one. And then not as common, we have two-phase generation. So to get it still takes 180 degrees to complete sine waves, but we get two sine waves out of it. So for the same, if that north-south magnet is the same weight for both generators, has the same friction, same moving force, we are getting double the sine wave output for the same amount of work. So we've doubled our output sort of based on nothing more than adding more windings around the outside. And this is what that sine wave would look like. And then you have three-phase generation, is what we would most commonly see. Okay, so this is taken from the engineering mindset. So if you want to hear a good explanation in video format where you can just sit there and watch, they do a good explanation of three-phase electricity. I would put it up. I just have to edit the video. Cool. So that's the main reason we use three-phase is for transmission and generation, is because it is the most efficient way to generate. We could add more phases, but at that point we get diminishing returns the more phases we add on top of that, and our generators would need to be so large they would be hard to get to rotate and thus generate electricity. Cool, so we're going to open the three-phase generator. So this is with only one winding, two windings per phase, because you need a north-south positive negative. So here on the left, we have three-phase circuits, and then on the right, we have a star-connected generator. We will talk about star and delta shortly. And so this is what our sine wave looks like. So we have three even sine waves. So it looks like we have quite even power or voltage generation. So if we were to put that next to a voltage plot, benefits in the module of three-phase is the ability for at least 7 different consumer supply options over 4 conductors. Huh? Okay. Okay. 7 different supply options. Cool. So I don't see 7. I can, only see 3-phase, 2-phase, and single-phase combos. So you've got 3 phases, so that's 3. Then you've got 2 2-phase options, so that's 4, 5. And then your three-phase delta and three-phase Y. Cool. So let's see if I can find a pen for this thing. Cool. So theoretically, you would have your red, white, blue delta. This is without a neutral. Then you would have your red, white, blue star. This is with a neutral. Then you would have red, white, blue. It's 1, 2, 3, 4, 5. Red, white, white, blue. And then I suppose you could also count blue and red. I don't know where they're getting this information from. Yeah. I'm not consulted when they develop any of this material, but that's probably where I would go with that. Generally, your main source of types of supply for your three-phase is going to be three-phase delta, three-phase star, or single phase or two-phase. So 4 options really. So unsure of where they're getting that 7 from. Cool. Cool. So some of the benefits for three-phase. So we've got more efficient transmission and generation, so less conductor material and less volt drop. So because we've stepped up increased the voltage with 400 volts, we've decreased the current. So therefore, we're getting less loss and less volt drop, because as we looked at last week, volt drop is dependent on amps per meter. So how many amps? That's probably what they're going for, Timothy, yeah. Because they're not counting star or delta. Cool. We would have a smoother power delivery, so it extends equipment life because it's a much smoother. We don't have as much volt drop in the forward reverse direction. So for motors, we get more power, they're self-starting, and they're more reliable. So we don't have to use extra equipment to start our motors. And three-phase machines are generally cheaper and more efficient, so less power wastage. And single-phase alternators cost nearly as much, but deliver only a third of the output. The other thing with three-phase machines is if you can run all 3 phases are relatively equal, you get charged less because you're wasting less power. So one thing to remember on a system, so if we're running cool. If we have on red phase 80 amps, on white phase, we'll use yellow, 54 amps, and on blue phase, let's say 48 amps. We still have to generate 80 amps. So we still have to get that generator moving at 80 amps or at we still have to be generating enough to create that 80 amps. So, drawing 80 amps down the red phase, we still have to generate enough power for 80 amps on yellow and blue. So all of this extra current or power is therefore wasted. So we still have to pay for that. So if we don't balance the load properly, we can be charged for it. Same goes for your power factor, which we'll talk about later. Cool. So here are some things to take note of. So on the system side, so the three-phase, it needs less conductor material to transmit same power as single phase. So it means a lower cost for the lines company, which then in turn means lower cost for the consumer because they don't have to pay as much in line charges. More efficient over long distances with less volt drop. And because the load current is shared across three phases, it balances out better. The system can handle much higher power capacity, which we rely on for industrial and commercial supply. And another big plus is that three-phase gives us smoother power delivery, which reduces our flicker and surges. And finally, allows us to offer multiple supply options. So single phase, two phase, or full three phase, all from the same network. So that's they're probably talking about what you're talking about. Red, white, blue, red, white, blue, and red, white, blue. And then on the motor side, so the reason we care about the motor side is because a lot of our industrial machinery still operates on motors. So a lot of manufacturing is where our biggest use of electricity is, and that is what powers our motors. So, no, they're still 120 degrees apart. But yeah, they are 120 degrees apart no matter what, unless it's only 180 degrees apart if you're generating two-phase. It's usually very rare in New Zealand to find a machine that operates on two phases. It's generally only in America that they operate on two phases. So in America, they operate at 110 and 220. So a lot of their bigger appliances use 220, which uses two phases. So it's a lot more common in America to have a two-phase supply to a house. The motor side, three-phase motor produces more power for same or smaller size. Design is simpler and more reliable. There's fewer components that can fail. And they also run much more smoothly with less vibration and mechanical stress, which helps them last longer. When you guys come to do your block course, you will be hooking up motors, including single phase and three phase, and you'll hear that the single phase motors sound a lot more angry when we turn them on. Cool. So less mechanical stress, which helps last longer, and they can also be made to be much more powerful. So self-starting. So, where's my mouse? Cool. So most motors of three-phase are self-starting, which means we don't have to use external devices. And so they actually work out cheaper than single-phase. And much more efficient to manufacture, making them the preferred choice for industry. You can technically make a three-phase motor run on single-phase supply, but it is still not as efficient or as powerful. Cool. So not every consumer needs a full three-phase power, but sometimes single-phase just isn't enough. That's where two-phase supply comes in. So some larger homes and small businesses are connected to two of the three phases instead of just one. This allows the consumer to draw more power than normal single-phase connection and handle. The main advantage is capacity. So, for example, homes with high demand appliances, it's like EV chargers, large heat pumps, spa pools, multiple ovens, induction ovens, may need more than a single 230-volt supply can deliver. Taking two phases provides extra supply without needing the full expense and infrastructure of a three-phase installation. Cool. Another advantage, voltage stability. Because the load is shared across two phases instead of just one, there's less chance of the voltage dropping under heavy demand. It also helps the electricity distributor by spreading the load more evenly across the network, and it gives better load balancing. So in a purely single-phase neighborhood, if everyone is drawing from the same phase, it can overload that part of the network. Splitting up consumers across two or three phases balances this out and keeps them more stable. So, two-phase appliances. So the majority of two-phase appliances that you'll find here in New Zealand still have a neutral conductor. So they're not 400-volt appliances. They are 230-volt with two feeds. Cool. So anyone give me a situation where they've had to do more than single phase? Obviously, you guys on the network all the time. Mains for a farm, yeah. Motors, distribution board in a warehouse. Oh, yeah, industrial motors. Anyone think of a situation where they might need two phases? Solar battery systems? Yeah. $480. Transformer, that would probably be a specialty transformer. Ovens, fridges, no. Fridges, unless it's like a chiller, fridges should generally just be single phase. I've said a couple, you guys can just say them back. Yep, commercial buildings. Water pumps, two phases, common out in the WAPs. Okay. Heater, like big industrial heaters, yeah. I think the only two-phase installation I've worked on that wasn't three-phase was a boarding house in Wellington, because they didn't have enough for three-phase, but they had enough for two-phase. So again, common, neutral, everything's 230 volts, no 400-volt appliances, just the extra capacity of having two phases. That's the main reason we use two phases here in New Zealand. Obviously, overseas, they do things a little bit differently, especially in America. Cool. So So far, we've seen how electricity is generated, 3 coils and an alternator. They are spaced 120 degrees apart. Because obviously, if you take 360 and divide it into 3, you get 120 degrees. Each producing its own AC sine wave. That's our 3-phase supply. Cool. Here's the key question. How do we actually connect 3 windings to make a usable system? So we don't just use 6 loose wires hanging out of a generator. We need to join them in a way that makes sense for distribution and for loads. This is where configurations come in. So the same 3 windings can be joined together in different ways, and each way changes the properties of the system. We've also already talked about a couple of them, or the 2 that we use. Delta end to end, yep. Yeah. The voltages, the currents, and whether we get a neutral point. So this is where the idea of configurations come in. So 2 most common configurations are star or Y and delta, yeah, or a triangle. Cool. So in star, one end of each winding is joined together at a common point called the star point. Gives us our neutral conductor, creating a 4-wire system. In delta, each winding is joined end to end in a triangle shape. This gives us a 3-wire system with no neutral. So we were to draw them out on the board. Cool. So for our star, we have our red. I'm going to use green. Black's going to be our white just because it's easier for you to see. And we have our blue. Okay. And at this point in the middle creates our neutral or our star point. So that is how we draw a star connection. And then we have delta, as Daniel pointed out, is joined. Oh, that's horrible. End to end. And basically a triangle. Why we call it delta? Because if you look up the Greek letter for delta, it is a triangle. That is where we get star and delta. So obviously, in star, we have a common point, which gives us our neutral. However, in delta, we have no common point. We only have our 3 taps off. So, go back to black. Between this point and this point, we have 400 volts. Standard low voltage. Standard 3-phase. That gives us our 400. Between these 2 points here, we have 400 again. But between our neutral and our other end of our winding, we have 230 volts. So whenever we're dealing with delta, it's always 400 volts. When we're dealing with star, it's 400 volts between phases and then 230 from phase to neutral or across one winding of the transformer. We will look a bit more in detail about transformers later, but for now, we're just talking about the national grid supply. Cool. So the choice between star and delta affects the relationship between line and phase voltage. So our line voltage, okay, I should have just left the board up. So, okay, so line, fuck off. So we think about line is what comes from the street. So that is our line voltage. We think about our phase as the winding itself. Okay, so our line voltage or current is what is in the transmission lines, or the line feeding our motor, feeding our oven, our industrial crusher, whatever we're doing. Our line is what's coming from the point of supply to the installation, to the machine. Okay, it is the transmission line or the street. Our phase is what's in the winding or in the load itself. So our phase voltage or phase current is what's in the. We will come back to that. I'm just trying to get some terms down first. So I will come back to star configuration and how the different voltages work, as well as we'll talk about current and delta, because there's a relationship there that you guys need to understand. But I want to get this down first, so that way when you come to do block course or answer questions on it, you know, okay, they're asking about my line voltage, it's the supply. The phase voltage, it's what's in the winding or in the load. So obviously, if we're measuring line voltage in delta or phase voltage, we're always measuring from either one end of the winding to the other, or between the connection points of each winding. So we're always going to get 400 volts in delta, because no matter what, we're always measuring the line voltage. Whereas in star, the line voltage is between phases, so we're measuring the lines. Whereas phase, we're measuring from one end of the winding to the other. We're measuring from one end of the winding to the neutral. So that's why we have the 230 volts. And I will explain that relationship in a little bit. Yeah, so star with a neutral lets us single phase consumers at 230 volts and three phase at 400. But delta always plays a big role, especially in transmission and motors. So the big idea here is the way we connect three windings changes that system. Star and delta are just two different methods of joining the same three coils, and both are fundamental to how electricity is delivered and used in New Zealand. Cool. If you measure one phase to neutral, yes. So if you measure from phase to phase, you get 400. You measure from phase to neutral or phase to earth, you will always get 230 on a standard site. That is because if there is a neutral, it's a star connection. Because star is a lot more common. Yeah, so the lines, guys, and residential definitely, because please correct me if I'm wrong, guys who work on the distribution network, but most of the transformers in the distribution network are delta star. So we can create that neutral or the earth point for the transformer. So when we're supplying the end user, it is more pretty much always going to be a delta star. So if you look if you've got power lines anywhere near you, there's usually two sets of lines or one. Or sometimes three. If there's one really high thin set and there's only three, that's your HV or your domestic residential kind of high voltage. Then that goes down into the transformer, which will spit out 4. Delta is the high voltage, star low voltage. Yeah, best explanation. Cool. Thanks, Daniel. See ya. If you look on the street, you'll see 3 lines going up. That's your high voltage on a residential site. supply and phase voltage. So the line voltage, again, would be between any two phases. So between red, white, white, blue, blue, red. Your phase voltage is red to neutral or red to ground, blue to neutral, blue to ground. That's how you tell the difference. But generally, it will be 400 and 230. So I draw those, well, I'll draw them without colors, make life a bit easier. So if we have our star and we, star, and we have our delta. So we have 3 points on each side, but on this one we also have the neutral point. So no matter where you measure this phase, you're always going to get 400 because it's always connected to the two other phases. So you're always technically measuring two phases. Whereas with star, I can measure between phases here, or I can measure between phase and neutral. So my phase and neutral is going to be 230. And again, we will talk about that relationship in a little bit. Yeah, there is some really good diagrams on there. I'm sure you guys are reading along as you go and are keeping up with it. Cool. So the reason we call it star in diagrams is because you join one end of each winding to a common neutral point. It kind of looks like the arms of a star or a letter Y. So if you look at any American material, it's called a Y, but they don't call it Y as in letter Y, they call it WYE. Cool. So start with 3 separate single phase windings and then connect one end to each winding together so it forms the star point. So if we look at an actual transformer, so we'll just do the one side. We've got our windings. Well, that's all right. 1, 2, 3, 4. Cool. So what we would do is we would take second of each winding and connect them together. And these would be connected to our, this would be a load, this would be a load, this would be a load, and then these would all connect back to the neutral line. So we've connected each side of the transformers together. Cool, but if we connected on the delta side, I know these are even numbers of windings. Cool. So it just is basically one long series. So you can almost look at this being in parallel, this being in series in terms of the way they're connected. The diagrams on the hive will be a lot prettier than what I can draw on this thing. Cool. So the star point can be connected to a neutral conductor, or it can just be connected to ground. Cool. So the other 3 ends are connected to line conductors. So you've got L1, 2, and 3. This gives us a 4-wire system, 3 phase and neutral, or 3 lines of neutral. Cool. Cool. So we turn off the whiteboard. Cool. So this is our star connection. So each phase winding is displaced by 120 degrees, and a load is connected across one phase in neutral. Then effectively only one phase winding is connected to and will apply an EMF. Cool. The magnitude and phase angle of this EMF is represented by the phasor, which is this phasor diagram. And we look at a mathematical phasor diagram point of view, there is only one phasor to consider, the phase winding. There's no angle associated in relation to the other phasors, so we don't worry about it. So the magnitude of the phasor is 230 volts. So you can see each winding is to scale, each is the same length, because each winding within the alternator would be the same length. Cool, so that's single phase, and this is polyphase, or two phase. So if we were to use, so you can see there, if we measure between phases, we get 393 volts. So 398.37 volts times the square root of 3. So we'll look at that in a little bit. So it's a polyphase connection. We cannot say that it's three-phase because we haven't connected it to three phases. But the same principles apply in terms of voltage level. If we were to connect the load, EMF being generated, and both of them applies to the external circuit, it's almost as if one bigger winding is supplying the circuit. But we can't just add the EMF values. Why can't we add the EMF values together? Anyone want to take a guess as why we can't just add the two 400 volts, 230 volts together and say it's going at 460 volts? Different load values? No. Nothing to do with the load. Yes, the angles. Yes, because of the different angles of the windings, yep, the peaks don't match. So the difference, the voltage level is not constant because it is peaking and troughing at different times in each of the three sine waves. So when the magnetic field is producing peak voltage in one winding, it is displaced from the other two, which has an effect on the overall EMF produced and must be resolved using phases to determine the value. So we could work this out using maths, by using Pythagorean theorem and angles, or we can use the square root of 3. So this is a relationship. So what I want you all to do is take 200, if we multiply 230 by the square root of 3, we get about 398 volts. But if we were to take 400 volts and divide it by the square root of 3, we would get about 229 volts. Thereabouts 230. So whenever we're dealing with three-phase and star, the voltage relationship is dependent on this. Cool. So simple explanation between two phases is that there is a resultant phasor that's 1.732 times greater than each individual phase. The easy way to remember this value is square root of 3. So nice and easy because three-phase calculation requires square root of 3 to be factored. So two terms we must identify. So phase voltage measured directly across one winding to be written as VPH, and then line voltage. The voltage measured across or between two windings. This can be written as VL. So the relationship is 3 minus square root of 3, and VL is always greater than V phase. I don't know what's going on with this PowerPoint, Therefore, we can adopt the following formula. In star or Y, voltage line equals the square root of 3 times voltage phase. This PowerPoint needs some editing. So another way to think of this are the installations we work with. In all three-phase installations have the following characteristics. All neutrals are joined together at the main neutral bar. There are two standard voltage levels, 400 and 230. Which means that the installation is connected in star. This cannot be achieved using the other connection method we will look at. So always remember the above formula. So all you have to do is remember in star, the voltage level changes between phase and line, and the relationship is always the square root of 3. So when we're talking about three-phase versus single phase, the relationship between phases is the square root of 3. Okay? Pretty simple to remember. Anyone struggling with anything I've said so far, please speak up. Anyone's got any more questions? Try not to quiz me on the material that's on the SCORM packet, because that is, I haven't delved too deeply into what they're telling you. I'm just teaching you what I know. Cool. Yes, if it was a delta installation or a delta connection, we would not set a neutral. So if you have a three-phase motor or a transformer connected in delta, you will see no neutral. See no neutral for that circuit. Obviously, in a factory, you'd run a neutral to a piece of machinery because maybe the machinery has some control gear that needs a neutral. So oftentimes you'll run three-phase to a control box with a neutral, and then you'll just tap off the neutral for the control circuitry, or sometimes you'll use two-phase 400-volt control. But yeah, in delta, no neutral. Cool. So when we talk about phase displacement, we must also take this into account in three-phase configuration. So the phase angle between voltage line and voltage phase can be observed as 30 degrees. So we make the triangle 120 degrees is between phases. All that's left over is 60. Therefore, each of the angles in the corners must be 30 degrees. Make sense? Cool. So this can be easily seen on the diagram between one phase and a line value. Simple justification for this fact is geometry. And all internal angles in a triangle add up to 180. The phasor or the previous page? I'm happy to go over something again, just I need to know which. Yeah, all good. So yeah, 120 plus 60 gives us 180, which are the internal angles of a triangle. So if we've got 120 phase displacement, then the last two must be 30 degrees. The phase displacement between each phase and the line voltage will be equal. This leaves 30 degrees for each angle. Sweet. Cool. Cool. So this is a simplified one for ease of remembering the relationship between phase and line values. So the phasor diagram represents all values at their max at the same time. But if we look at the time-lapse phasor that's on the screen now, it shows that all three phases peak and then fall at different times. So they're constantly moving as the phase value rises and falls. So here we've got phases A, B, and C, which can be seen as red, white, and blue. And this is our resultant R. So we've got our voltage going up to about the 1 mark, which might be our 230. but the black or the resultant R, which would be our line voltage, sitting at about 1.5. So the 400 volts is greater than each, but not the sum of each. So the sine waves are constantly going up and down, up and down, up and down at 50 hertz. And so at any one point, we are getting 400 volts, but no phase is actually sitting at 230 volts. They're always sitting at 230, at least in standard installations. And the resultant 400s is because of that phasor relationship. Remember, all you need to remember is square root of 3. That is the relationship between phases. Cool. So in star, voltage line equals the square root of 3 times voltage phase, should be pH. Cool. So we can see how each of the voltages are measured, phase to phase in dark blue, phase to neutral in purple. As we talked about before, phase and neutral is 230, and between phases is 400, which also equals the calculation we were looking at before, but with numbers added. So here is our star-connected transformer on the left, and here is our star-connected load on the right. This would probably be our star-connected motor. And you do sometimes connect a motor in star, but more often than not, it will be delta. We'll look at motors in a later topic a bit closer. Cool. So keep in mind, current draw is dictated by the load and voltage applied. When red phase is at its peak, the load connected to red phase will draw the max current. Current is returned through the other two phases in the opposite direction. Because the EMF values of white and blue phases are equal and in their negative half cycle. So in star, the line voltage is the same as the phase voltage. So in star, I line is equal to I phase. So the current flowing through the line is the same flowing through each phase. Cool. So with current, Ohm's law teaches us that given impedance or resistance will cause a predictable amount of current to flow. It depends on how the load is connected, on how much current will flow in the lines and through the load. So why would they be different if the load impedance is always the same? Because current flow is also dependent on the amount of force applied to the circuit, so the amount of voltage being applied. So depending on the circuit configuration will depend on the voltage applied to that load. We can also look at a series parallel situation. The load is in series with the phase winding and line conductor, so we'll receive maximum current. Once it's passed through the load, it reaches the start point. It will split as current does in parallel circuits. So for now, star configuration is easiest to remember the difference between phase current and line current. There is no difference. So flows from the start point through the phase winding, through the line, through the phase load to the neutral point. So at no point is there a parallel path on that phase until it gets to the other two phases. So it is in series and therefore current remains the same. Does that make sense? I know I'm giving you guys a lot of information. Hopefully some of it is making sense with what you guys have read online already. It is a big topic. Obviously, it's quite a bit of a step up from year 1 to year 2. And I'll warn you guys now, the step up from year 2 and year 3 is just as big, which means also we want more information when you give answers to the online questions. The more information and detail, as long as it's accurate, the better. That way there's less excuse for us to go, no, try again. So yeah, load current is labeled I phase here, as well as the supply winding, because in a transformer, we call the current flowing the primary winding primary phase current. Cool, and this is what it would look like. So these are two ways of drawing the same diagram. So this is what you would normally see on a drawing. So this is a simplified drawing, so we can see all the connections between A, B, C, and A1B, 1C1. But this is a more accurate representation on the right of what the windings actually look like. So you can see the black lines here, which is our common neutral point, and then we have our blue, grey, and red, or our blue, white, and red, white, and blue, whichever way you want to go, winding connections for our star transformer. Cool. Anyone got any questions about star connections before we move on? I know we're talking about transformers here on the board, but it's the best PowerPoint I could find for this topic. Cool. Don't be afraid to ask questions, guys, because odds are if you're thinking about it, someone else is too. And again, I don't mind answering questions. I know it's going to make night class longer, but I would rather you guys leave with as much information as possible. Cool. So the next one is delta configuration. Cool. So the reason we use star, just a few things to cover off. So provides 230 and 400 volt supplies with one system. The neutral provides a return path and allows for effective earthing through the MEN system, which we'll talk about later. And star with neutrals is the standard in New Zealand distribution. And we can have balanced loads to reduce stress on the system. So we don't have to supply three phase to every house, and not every house has to have use three phase. Because if any of you guys have done a three phase installation, domestic installation, you'll know that load balancing is very difficult, especially because you can never predict who's going to use what. And if you do an installation like I've done in the past, where it's 100 and something switchboards all using three phase, you can't guarantee that the rotating of the phases from unit to unit, house to house, board to board has been done correctly. So if you wired an entire block with all of the hobs and ovens on red phase, you would cook that phase pretty quickly. So there's a little bit more detail needed to use. Cool. So delta, which is what you can see on the screen. So we call it delta because of the Greek letter, makes it look like a triangle. So in the delta connection, the three-phase windings are joined end to end, end to start, forming a closed triangle loop. The triangle shape in the diagram is why we call it delta. So imagine the three separate single-phase windings. Instead of connecting each one to a neutral point, like in star, you connect each end of the winding to the star of the next all the way around, creating a closed circuit for all three coils, almost like it's connected in series. So the three conductors, L1, 2, and 3, are taken from the three junction points. So you've got red, L1, white, yellow or blue, L2, and blue, L3. So delta has no neutral, like we've covered before. It is a three-phase, three-wire system. Cool. So the other possible configuration you'll come across for three-phase. So delta tends to be more prevalent in transmission and distribution networks on the high voltage side. It is uncommon to see an alternator or the consumer side of a distribution side of a supply configured in delta. So delta configuration can also be referred to as mesh configuration, but either way, they represent the same thing, symbolized by Greek letter. And we've talked about the way they're connected to form a triangle. Cool, so connecting to a delta supply, so like a star configuration, each phase is still 120 degrees displacement from one another. Key difference for delta is though there is no capacity for a neutral connection, any load connected to a delta configuration supply must be balanced. Motors are suited for this as all three windings are the same impedance and draw the same current. So in balanced system, any voltages at any point will equal zero. So a simple example of this is that when any one phase is at its peak, the other two will be in their negative half cycle at half of the peak value. So when red phase is at 230, white will be at negative 115, and so will blue. The sum of these voltages equals zero. This is why the case when impedances and current flows are equal, but obviously they're not always going to be. When they're not equal and there is an imbalance in the system, a potential can exist and cause circulating currents to flow. If the impedance of the circuit is low, excessive current can flow, causing excess heat and damage to the supply. Installations cannot be connected to a delta supply as it cannot be guaranteed that loading will be balanced. So it is very rare that you will ever see a mains connection in delta, simply because we cannot control whether the load will be balanced at any one time. So we still need a neutral point for that current to flow back to the other phases. Cool. So voltage. So unsurprisingly, because we have no neutral connection, everything is 400 volts. So in delta, voltage line equals voltage phase because we have no neutral, so therefore we have no difference in potential. So it's more common to see transmission and distribution lines connected in delta. So you'll notice this if you look up at a power line, you'll only see a set of 3 conductors for the most part, although it's not guaranteed. It's very probable that they're configured in delta at high voltage level. You may see underneath them a set of 4 conductors. This will be the consumer supply, which has been transformed to 230 or 400. Although obviously if you live in an area where it's all underground, you'll see nothing. Cool. So the 4th conductor will be the neutral return. So the most important part to remember about this is that voltage line and voltage phase are equal. Well, getting there. But current. So current is the thing that changes. So when a 3-phase load is connected in delta, so the load is connected in parallel because it has 2 paths to go to. So if you look at the connection points, current flows into the load by a single conductor, but then splits in 2 when it flows through the individual loads. So just as we started voltage and star, it's not quite the same as adding the values together as they're 120 degrees displaced. However, just like in a basic circuit, when we've looked at previously, more current will flow on the supply conductor and then split as it reaches the branches. So due to the phasor displacement, the relationship between the current flowing through the load, phase current, I phase, and the current flowing through the supply lines, line current, IL, is again 1.732 times, or a factor of square root of 3. So we use this formula for star. I line equals the square root of 3 times I phase. So I line is greater than I phase to a magnitude of the square root of 3. So whenever we're talking about 3-phase, for calculations, you always need to include the square root of 3. So you just have to remember, in star, it's the voltage that changes, and in delta, it's the current that changes. These will come very important when you do transformer questions. Transformers make up a pretty significant part of the capstones that you guys will sit at the end of this year, and is where you can get the most marks for the most part in the transformer questions, because they will be multi-layered. But for now, we just need to remember that this is the relationship between star and delta. Cool. And this is a delta. So on the left, we've got the symbol of the triangle. And obviously here on the right, we've got the actual physical, how it would be wired up. So you can see we've got a tag off of each winding, but all the windings are connected together in a series loop with taps off at each point. So that is our delta connection. And then as you, obviously the network guys will know, so this would be star delta. So you see on the left, we have a common neutral point, and on the right, we have series windings connected together. Delta star is just the opposite. Cool. So one key factor to take into account when direct conversion occurs, there's a 30 degrees phase displacement between the primary and secondary phases. This is not an issue in an independent system, as the primary and secondary circuits would never be connected. However, in a wider scheme of things, it can be potentially dangerous because if it occurs in a system that has had other configuration methods and other transformers, it can cause a difference between these parallel circuits, and we can get circulating currents to form the system. Cool. Correct me if I'm wrong, line guys. Common relationship used in New Zealand's delta star transformer is DY11. This is where the circuit configuration is laid out on a clock face. The point of the triangle and the primary delta will be at 12. The tip of the star winding is placed at 11. This represents the 30-degree phase displacement between primary and secondary windings in this configuration. So, some more key facts. Cool. So, why we use delta? Transmission efficiency. It allows efficient power transfer over three conductors without needing a neutral. Many three-phase motors are connected in delta to allow them to operate at higher line voltages, which delivers more torque, as we'll look at when we do more on motors. Redundancy. If one coil in a delta system fails, the system can still operate in open delta, though at reduced power. Oh. Okay. Yeah, so watching the video, pause now and take note of these. So, star connection. So these are all the different points that we've covered off tonight. So, I won't get you guys to write these down now, but do go back and watch the video. It'll be posted. Actually, if you're on the computer, take a screenshot. Take a screenshot of these now, and then you can copy them out later. Anyone not able to take a screenshot? Let me know when you have in the chat if you're taking a screenshot. This is a good, helpful thing to keep a note of. Oh yeah, Timothy's just posted a screenshot in the chat. Nice. So key points to remember: the square root of 3 relationship comes from the geometry of the three-phase windings. A star connection, line-to-line voltage is greater than phase to neutral. The exact factor is the square root of 3, which comes from the 120-degree spacing between phases. This is why we have 230-volt line neutral and 400-volt line. Cool, and we looked at the geometry of the square root of 3 factor. Certainly can. Cool. So we'll talk about the current. So the reason in star that current is the same as in the line and the phase, because if we look at, this is our phase current. It is inside the phase winding. This is the distribution line, and then this is the phase load. They are in series. So current in a series circuit always remains the same. So if the current flowing through this phase, through this line, and then back through this phase are the same, we must are in series, it must be the same. So therefore we say voltage phase and voltage line are the same. And then the relationship between the voltage line and the voltage phase. So we were to take this example. So we'll back up. Come on. Cool. So we've got our diagram here. So if we use that as an example, we've got our Y here. We've got our voltage line here. So we've got our 30 degrees here. This is our 230. So we would divide this in half. So we've got 230 as our hypotenuse. Using Pythagoras' formula, what would our adjacent be? Or in this case would be half VL. So we're working with adjacent and hypotenuse. So it would be cosine. So CAH, CAH. So we want to work out A. So it would be cosine of the angle times the hypotenuse. So it would be cosine 30 times 230. What does that give us? Now it means you've got to grab out your calculators, but what does that give us? 200? Yeah. Which gives us 200, which we need to multiply by 2, which gives us 400 volts. Pretty straightforward, right? Does that make sense, Sean? And then if we wanted to figure out, yeah, silly headache. And then if we wanted to figure out also so the cosine of 30 equals the A divided by H. So A is 230, H is 200. What is 230 divided by 200? Never mind. Doing the math wrong again. Don't worry about me. Okay. Don't worry about that last one. That was just me getting my maths mucked up again. Don't worry about it. Yeah. So after a while, you will kind of just accept this stuff as being the way it works after you do the calculations a few times. The square root of 3 factor isn't magic. It comes directly from the 120-degree separation between phases. Explains why our system gives us 230-volt line and everything. Cool. So, how is three-phase power generated in an alternator? Give me a best brief explanation about how that works. Yep, you've got parts of the answers there. Cool. So by rotating a magnetic rotor 360 through 360 degrees, 3 separate coils positioned 120 degrees apart, each produce an alternating voltage. Together they form 3 out-of-phase waveforms, or the 3-phase system. Yeah. Cool. So each phase winding of a star-connected system produces 230 volts. What will the line-to-line voltage be? I want everyone to answer that. And what is the relationship between phase and line voltage and star? I know everyone else will answer it, but I just want to see everyone put something into the chat, so that way I have a way to say, yep, they definitely were here. Yep, and what's the relationship? Yep, 398.37 volts. Yep. Yeah, so the relationship is the square root of 3, whether that be multiplying or dividing by. It is still, the relationship is the square root of 3. So what is the key difference between star and delta connections? Yep. So 3y delta, 4y star, and the star has a common point. Yep. So with star, one end of each coil is joined at a common neutral point, allowing both line to line and line to neutral voltages. And in delta, coils are connected end to end in a closed loop, giving only line voltages. Cool. So why do some large homes or small businesses use two-phase instead of one? Yep. To power bigger loads. Yep. More capacity, load sharing. Yep. Yep. So two phases provide a higher capacity than single phase, and it gives better voltage stability, and it helps with load balancing compared to one phase alone. And so why do we use square root of 3 in these calculations? I like it, Daniel. I like it. Yeah. Because the phases are 120 degrees apart, when calculating the vector differences between two phases, the result is square root of 3 times the phase voltage. This geometry explains why New Zealand has 230 volts phase to neutral and 400 volts line to line, and why America has 110 and 220, just because they operate things differently. Cool. So thank you for being part of this lesson. And if you guys have no further questions, you are welcome to log off for the night. I will quickly stop the recording.